You know, keeping a binary search tree balance is one of those classic computer science problems. And most of the time, the solutions involve these really complex, rigid rules. But what if we could get the same awesome result with just a simple, elegant dose of randomness? Well, that's the whole idea behind the Treep. And today, we're going to break down exactly how this clever little data structure works. Seriously, if you've ever tried to code up an AVL tree or a red-black tree from scratch, you know the balancing logic can be a total nightmare. I mean, they're incredibly powerful for sure, but all those different cases and rotations are just so complex. It kind of makes you wonder, right? It leads to this brilliant what-if question. Could we get that same amazing performance, but with a much, much simpler randomized approach? And that's exactly the problem the Treep was invented to solve. The name itself is really the first big clue. Treep is a portmanteau, a mashup of two words, tree and heap. And that's because it cleverly fuses the properties of a binary search tree and a heap into one single elegant data structure. It's a two-for-one deal. So what does that actually mean in practice? Well, it means every single node in the tree is juggling two different values. First, it has a key, and that's what keeps everything sorted, just like in a normal search tree. But it also has a randomly assigned priority. And it's this unique combination of an ordered key and a random priority that really unlocks the Treep's power. Okay, so to make this whole thing hang together, a Treep has to follow two golden rules at all times. Think of them as its core principles or invariants. These two rules define its entire structure and behavior. This slide shows the Treep split personality perfectly. It's amazing. If you completely ignore the priorities and just look at the keys, that's the left side, what you have is a perfect binary search tree. Everything to the left of a node is smaller, everything to the right is larger. Simple. But now, if you ignore the keys and only look at the random priorities, as you see on the right, you have a perfect min heap. Every parent's priority is smaller than its children's. And here's the kicker. Both of these rules have to be true for the entire structure, all at the same time. Right, but what happens when we want to insert or delete a node? I mean, that could easily break the heap property, right? Well, the Treep's secret weapon for fixing this is a surprisingly simple operation, the tree rotation. The insertion process is actually incredibly intuitive. Here's how it goes. First, in step 1, you just pretend the priorities don't exist. You insert the new node based on its key, just like you would in any standard BST. Easy. Then, step 2, you check, does this new node's priority mess up the heap rule with its parent? If it does, we move to step 3. You perform these simple rotations to bubble the node up the tree, swapping it with its parent over and over until that heap property is fixed. And here is the absolute magic of the whole thing. This is the critical part. These rotations are designed to be, well, surgical. They fix the heap property by changing who's a parent and who's a child. But they do it in a way that perfectly preserves the sorted order of the keys. So even as the tree's physical shape is changing, the binary search tree property remains totally intact. It never, ever breaks. Okay, so we have a slick way to maintain the rules, but we still haven't answered the big question. Where does the balance actually come from? This is where that randomness we talked about becomes the magic ingredient. Okay, check this out. This is the beautiful insight. Because of the heap rule, we know that nodes with smaller priorities are forced to bubble up. This means that the node with the single smallest priority in the entire set is absolutely guaranteed to become the root of the tree. The one with the next smallest priority and its part of the tree will be its child, and so on. What this effectively does is create a structure that's statistically identical to what you'd get if you just took all your keys, threw them in a bag, shuffled them up into a random order, and then inserted them one by one into a standard BST. That randomness is our built-in defense against the worst-case scenario of getting a long, stringy, unbalanced tree from sorted data. And the payoff for all this cleverness? It's exactly what we wanted from the very beginning. Fantastic performance. Because that randomness saves us from those nasty, degenerate trees, the expected time complexity for searching, inserting, and deleting is O of log n. Let's just quickly highlight the key performance metrics here. So, as you'd expect, the tree's height on average is logarithmic. But here's the part that's truly remarkable. The number of rotations you need to do to fix the heap after an insert or delete is, on average, a constant number. We're talking 0.1. It doesn't matter if the tree has 100 nodes or 100 million. The fix is expected to be just as quick. Now, of course, we have to mention the fine print. An extremely unlucky series of random priorities could still lead to a worst-case ON tree, but the odds of that happening are just astronomically low.
All right, so knowing how a tree up works is one thing, but when should you actually use one in the real world? Let's talk about the practical trade-offs and, what you really need to know if this topic ever comes up in a technical interview.
This comparison chart really gets to the heart of it. A Treaps balancing is all based on randomness. Trees like AVL or red-black, on the other hand, are deterministic. They follow strict rules. This means Treaps give you expected O-log n performance, whereas the others give you a hard, ironclad, worst-case guarantee. So what's the trade-off? Simplicity. Treaps are way simpler to implement, with a lot less code and fewer tricky edge cases to worry about. So, if you need a cheat sheet for that interview, here it is. First, you have to nail the explanation of the two invariants. It's a BST when you look at the keys, and a heap when you look at the priorities. Second, you have to justify its awesome performance by connecting those random priorities back to the idea of a random insertion order. Third, that killer performance detail? The expected number of rotations is constant time, O1. And finally, be ready for practical questions like, how would you handle duplicate keys? A really common solution is just to add a counter to the node. And that really leaves us with the fundamental question of the trap. In a ton of real-world applications, being almost always super fast is more than good enough. It all boils down to a classic engineering trade-off. Is the elegance and the beautiful simplicity you gain from randomness worth giving up that absolute deterministic guarantee against the worst possible case? Definitely something to think about.